Hello everyone, welcome back. In this lesson, we're going to start to talk about a procedure called vector projection. Vector projection is a procedure that allows us to take a vector and split it into two parts. Split the vector into one part that's parallel to a given surface and one part that's perpendicular to a given surface. It's basically vector addition in reverse. And let me explain what I mean by that. When we introduced vector addition, we talked about how there is a triangle rule, where if you have a vector v and another vector w, then the sum of these two vectors represents the direct path from this initial position at the tail of v to this terminal position at the head of w. This is the vector v plus w. So in this instance, we're taking a vector v that might lie parallel to some surface, and we're taking the vector w that might lie perpendicular to that surface, and we're combining those two vectors into a single result. What we're going to do in this section is essentially take this process and perform it backward. We are going to start with a surface, and we're going to start with a vector that's coming out of that surface, perhaps diagonally. And then we're going to take this vector and break it down into its parts. We're going to take this vector and break it down into one part that is parallel to the surface, called the projection. The projection of V onto the surface. And then we're going to have this sort of leftover extra part, which is perpendicular to the surface. Taking a vector and splitting it into parts as opposed to taking two vectors and combining them into a single result. To give you a quick real-world example of why you might want to do something like that, why you might want to take a vector and split it into parts like this. Imagine the following sort of physics problem, where I have an object that's sitting on a tilted or inclined surface. So imagine that my surface is coming out tilted this way, and I have an object sitting on top of it. If I think about gravitational force acting on this object, gravitational force acting on this object would point straight down, the way it always does. Let me call this vector F sub g for gravity. I might want to take this gravitational force vector and split it into two parts. One portion of gravitational force that's parallel to the surface, and then another sort of leftover extra portion that's perpendicular to the surface. The reason that I might want to split the gravitational force vector into these two portions is that these two portions are having very different effects on the object in this problem. The projection here, the portion of gravity that actually is parallel to the surface, is the portion that would actually have the effect of potentially sliding this object down the surface and moving it along the surface. Whereas this perpendicular portion that's driving the object into the surface is going to contribute, for example, to friction and to resistance. This is going to contribute to what we call in physics the normal force in this problem. So this is what projection will allow us to do, to take a vector and split it into two separate portions that we might want to study separately, because those two separate portions of the force might be having very different effects within a physical context. So to that end, we're going to define a certain formula. So the formula is for the projection of a vector v onto a vector w. If I'm projecting a vector v onto a vector w, the notation for that are the letters P, R, O, J, short for projection, then a subscript representing the vector that we are projecting onto. Then next to that, the vector who is being projected. If I'm projecting the vector v onto the vector w, the formula for that is as follows. The first thing that I'm going to do is find a scalar multiple. And the scalar multiple that I'm going to find is equal to a fraction where v dotted with w is in the numerator. And then the squared length of w is in the denominator. So to emphasize, this quantity here in the parenthesis is a scalar multiple. Because v dot w produces a scalar, the dot product always produces a scalar, and the length of w is a scalar as well. So both the numerator and the denominator here are scalars. I'm going to take that scalar multiple and I'm going to apply it to the vector w. So scale the vector w by this number. That's what the projection is asking us to do. The first thing that I want to note is that the projection onto the vector w, the result of that calculation, is going to be parallel to the vector w. And this follows from the fact that when we project onto the vector w, the projection onto w is a scalar multiple of w. And when we scale a vector, there's a limited number of things that can happen, right? If the scalar is positive, then that is going to change the length of w without changing its direction. If the scalar is negative, then that's going to flip w's direction. But in either case, the answer is going to be parallel to w. The answer will lie on the same line as w. So that's the first thing to keep in mind. If you're projecting onto the vector w, the result is always going to lie on the same line as w. The second interesting sort of property of the projection suggested by this formula is that the final answer is completely unaffected by w's length. And that follows from the fact that the formula contains two instances of w, the w here in the dot product and the w here on the side that's being scaled. And we are also dividing out two copies of w's length. So that means that this W is being divided by its length. This W is being divided by its length. So both of these W's in the formula are being converted to unit vectors. So that's why the length of W doesn't matter. No matter what length it has, that length is just getting divided out anyway. So it doesn't have an effect on the result. So let's go ahead to a GeoGebra interactable and see what the projection looks like for a variety of different vectors v and w. I have a vector w that I'm projecting onto, and I have a vector v who is being projected. I'm projecting v onto the vector w. So I can go into this picture and I can make various adjustments to V and W to see what the projection looks like in various instances. So the first thing I want to draw your attention to is that W itself doesn't really matter. What really matters is this line or surface that W lies along. The line or surface that contains W is also going to contain the projection. And that is a consequence of the fact that we noted earlier that the projection onto W is always parallel to W. So we take the vector W and we extend it into an entire line or surface because that line or surface is where the projection is going to live. I can also see that no matter where V is positioned in this drawing, the projection forms a leg of a certain right triangle. Projection is the parallel leg in this right triangle, and then we have this perpendicular leg in this right triangle, and the vector V is forming the hypotenuse of the right triangle in this picture. So thinking about the projection, we're projecting onto the vector W. So we start by extending W into an entire line or surface. And then we think about the vector V as being the hypotenuse of a right triangle. A right triangle with one leg along this line or surface, parallel to this line, parallel to W, and another leg that's coming out of that surface in a perpendicular fashion. Remembering that the entire purpose of projection is to take a vector v and split it into these two parts, a parallel portion and a perpendicular portion. To make sure we understand what the projection formula is doing, let's go ahead and practice finding the projection just using a picture and not using the formula. So here, for example, is an image of two vectors, v and w. And the first thing that they're asking me to do is to draw the projection of the vector v onto the vector w. If I'm projecting the vector v onto the vector w, the first thing that I'm going to remind myself what really matters is the surface, is the line containing W, the surface or line that W represents. So the very first thing that I'm going to do as I begin to draw this projection is extend the onto vector into an entire line. So having now extended the onto vector into an entire line, I'm going to try to set up a right triangle within this picture. I'm going to try to set up a right triangle where the hypotenuse of the triangle is V and one leg is parallel to W. Let me go ahead and use the ruler tool to help me to draw that right triangle. I'm going to position the edge of the ruler at the arrowhead of V, and then I'm going to rotate the ruler until that ruler forms a right angle with this line and with this surface. So just about here is correct. Then I'm going to mark down a little line segment along that edge. Eliminate the ruler, and now I have formed a right triangle within this image. A right triangle where the hypotenuse is V, I have this dashed red line forming the perpendicular leg, and then down here I have the parallel leg. So this parallel leg of the triangle, this parallel leg right here, the parallel leg is the drawing of the projection. The projection of V onto W. Let's do the process again, but let's practice drawing the projection of W onto V. The very first thing that I'm going to do is I'm going to extend the vector V into an entire line or surface through that vector and extend that out. Now I'm going to try to create a right triangle within this picture. A right triangle where the vector that I am projecting, the W vector, is the hypotenuse, and one of the legs lies along this line. So let me bust out my ruler tool, and I will position it over here at the head of W, and I will rotate the ruler until I get a right triangle, a right angle here with this line. So let me mark in this perpendicular leg. And with that move, I have formed a right triangle in this corner here. A right triangle where the hypotenuse is W. I have this line segment coming perpendicular out of the surface, and then I have this piece parallel to my surface. So this parallel portion, the parallel leg of the triangle, is what the projection is producing. The projection in this case of W onto the vector V. Now let's go ahead and get some practice actually calculating the projection using the projection formula. Here I have a vector V equals 2, comma, minus 1, and a vector W equals 1, comma, 1. To begin with, let's project the vector V onto the vector W. So since I'm projecting onto the vector W, I'm going to need to start by finding V dot W. Then I'm going to need to find the squared length of W. And then I will use that to create a scalar multiple, which I apply to W. So V dot W in this case would be 2 times 1 plus negative 1 times positive 1. So that result is positive 1. And the squared length of W is going to be the x component squared plus the y component squared. So that's giving me a value of 2. Therefore, the projection of V onto W is going to be equal to the fraction 1 in the numerator, 2 in the denominator, being applied to the vector W. I get 1/2, comma, 1/2. Okay, here on the GeoGebra module, I've adjusted the vector V to point to the location 2, comma, minus 1, as in the picture. And I've adjusted the vector W to point to the location 1, comma, 1, as in the question. So the projection is this black vector here, the portion of V that is parallel to this surface, to this line created by extending W. And we can see that that black vector, that black projection, indeed does point to this location 1/2, 1/2, 0.5, 0.5 here in decimal form. Let's reverse the roles here, and let's project the vector 1, comma, 1 onto the vector 2, comma, minus 1. So now doing W dot V, that dot product in the opposite order is going to give me the exact same result as before. But now let's do the length of V squared, and the squared length of V is equal to 2 squared plus minus 1 squared, which is equal to 5. So I will construct the scalar multiple 1 over 5, and I will apply that to the vector V. And this is going to give me the portion of W that is parallel to V. So that would be the vector 2/5 minus 1/5. Okay, I've rearranged things a little bit. So now the vector who is being projected is pointing to this location 1, 1. And the vector that I'm projecting onto is pointing to this location 2, minus 1. So the vector that I'm projecting onto is the one that is representing this line or surface. And the vector who is being projected is the one that's getting split into portions. One portion that's parallel to this surface and another portion that's perpendicular to this surface. And what we can see is that the projection is pointing exactly to this location, 0.4 being equivalent to 2/5, 0.4 in the x direction, and negative 0.2 in the y direction. So the projection that we're finding graphically here is an exact match to what we found using the formula. Let's go ahead and return to that context from the beginning of the video, where we're taking a gravitational force and we're splitting that force vector into parts. One part that's parallel to a surface and one part that's perpendicular to the surface. We have a 5-kilogram object that's sitting on a tilted plane. The plane is inclined 20 degrees above the horizontal, and the object is acted upon by gravitational force. So let's find the portion of gravitational force that's parallel to the plane, and let's find the portion of gravitational force that's perpendicular to the plane. Now, the projection is designed to give us the portion of a vector that's parallel to some surface. The projection formula requires us to represent that force in vector format, and it requires us to represent that surface in vector format so that we can do things like dot the vectors together and calculate the vector length. So that's the first thing that I'm going to do in this applied problem. I'm going to represent both the force and the plane by vectors so that I can use that projection formula with the dot product and everything. So first of all, representing gravitational force as a vector. For a 5-kilogram object, the gravitational force vector would point straight down with a magnitude of 5 times g. So it would be negative 49 in the y direction. I'm also going to represent the plane as a vector. Call that vector u. I want some vector that represents the surface, some vector that is also inclined 20 degrees above the horizontal. So if this yellow bar is my horizontal and my plane is inclined 20 degrees above that, then I'm looking for a vector u that points in the same direction of the plane and makes the same angle with the horizontal. Now, because the length of this vector doesn't matter, because it's just representing the surface, because whatever length it has is going to be divided out in the end anyway, I might, for my own convenience, just go ahead and make it a unit vector and write down something like 1 cosine of 20 degrees, 1 sine of 20 degrees, using that polar coordinates formula that we established in a previous lesson. So I will use this unit vector as a representation of the plane. I'm going to project the vector f onto the vector u. That will give me the portion of the force that's parallel to the vector and in turn is parallel to the plane. So using the formula F dot U, that dot product based on these components would be equal to negative 49 times 0.39, because the x components would vanish because of the 0 here. That's roughly speaking 19.11 units. The squared length of U is going to be just 1 because we manufactured U to be a unit vector. And so now I have the numbers that I need to form the scalar multiple that is applied to the vector U. The projection of the force vector onto the vector U is going to be the number 19.11 over 1, scaling the U vector. Oh, excuse me. This is a negative result from the dot product, right? That's a negative result from the dot product. And that actually is going to be really important for this result making sense in the end. So that's a negative 19.11 being applied to the vector U. Negative 17.96, 7.45, again, negative. Now, let's put this vector into the picture and check see it makes sense in the context of what's physically happening. We have our gravitational force vector acting on this object, pushing the object straight down, vertically straight down in the negative y direction. And then I'm projecting this force vector onto the plane to find the portion of the force vector that aligns with the plane. So if I think about f sub g as the hypotenuse of a right triangle, where one leg of the right triangle is here on this plane and the other leg is sticking out perpendicular to the plane, the projection is that parallel leg right here. So this vector is our projection. So we can see that the projection vector, based on the picture, should point down and to the left. Down and to the left. And that's why it's important that we get a result with a negative x component and a negative y component. So that's why it was so important for me to correct this result right here. This dot product had to be negative in order for this answer to end up with negative x and y components, pointing down and to the left as in this image. So now that we found the portion of gravitational force that's parallel to this surface, now let's find the other portion of gravitational force, the portion that is perpendicular to the surface. To find the portion of the force that's perpendicular to the surface, I'm just going to use vector subtraction. I'm just going to use vector subtraction because based on the picture that I have f sub g here. I have the projection, and then this leftover portion in the corner is the vector I'm currently trying to find. Now, by triangle rule, the projection and the unknown vector in the corner, if you add them together, the total is equal to f sub g. So the vector that I'm trying to find, the perpendicular portion, is just equal to f sub g with the projection removed. So to that end, I can now fill in my gravitational force vector, 0, negative 49 from earlier, and I can fill in my projection vector, this quantity from earlier. And then I just have to finish doing the subtraction component-wise. So I get an answer of positive 17.96 and negative 41.5. 5, 5. So this vector points down because of the negative y component, and it points to the right because of the positive x component. That makes sense based on the picture, right? It makes sense based on the picture that this perpendicular portion points down and to the right. That makes sense based on the vectors in this image. That is where the perpendicular portion should be pointing. That concludes this video. We learned in this video about a tool called vector projection. In the same way that vector addition allowed us to take two vectors and combine them into one, projection allows us to take one vector and split it into two parts. One part that is parallel to a given surface, and another part that's perpendicular to that surface. The projection formula requires you to have two vectors, the vector that you are projecting and a vector that represents the surface that you are projecting onto. To project a vector v onto a vector w representing some surface, you can use the formula v dot w divided by the squared length of w, forming a scalar that you apply to w. This forms a vector that is parallel to W, the portion of V that is parallel to W. If you want to find or understand a projection graphically, you take the vector that you're projecting onto and you extend it infinitely into a line or surface in both directions. Then, on that picture, you try to draw a right triangle. A right triangle where the hypotenuse of the triangle is the vector who's being projected, and one leg of the right triangle lies parallel to the surface. You draw that right triangle, and the parallel leg is the projection that you're trying to find. The other leg of that triangle then forms the perpendicular portion. So using triangle rule, once you have found the projection using that formula, you can find the perpendicular portion of that vector just by taking the vector and subtracting the projection.